Now that we've reviewed some basic polynomial information that you probably learned back in Algebra 1, it's time to move on to some skills that will later help us solve polynomial functions. Now, you may remember from quadratic functions unit, the factoring skills, the completing the square roots, all of those were skills that we taught you with the end goal of trying to solve a quadratic function and come up with the solutions of the quadratic function. Well, now that we're moving into higher degree polynomial functions, we have to add some new skills to be able to solve polynomial functions later on when we get to that point. What we're going to do here is we're going to reintroduce the idea of factoring to you and show you how you can use these new factoring tools to solve some simpler polynomial functions that you may see, and then we'll slowly build on that progressively throughout the unit. Now, we start off here with a just basic recap of the different types of factoring that you can do that you learned back in the quadratic functions unit. So you can see basic trinomials, perfect squares, and common monomial factoring. And don't forget grouping as well. Now, what we want to add here is the first level of higher degree polynomials, and that's cubes. Well, just like squares, perfect squares, we can have a difference of two squares. We can have a difference of two cubes. But unlike squares, perfect squares, cubes can actually have a sum of two cubes. And you can see in this little special factoring patterns box, we show you the pattern. Now, the easiest way to do this and remember this pattern is through continued use. However, students in the past have used the acronym SOAP. Now, what SOAP means is that the first two signs are the same. The middle sign of the second the trinomial is opposite. And then the third sign is always positive. So you can see the SOAP acronym in that right there. And so maybe that'll help keep your signs straight. Now, the one thing that you want to pay special close attention to in the special factoring is the fact that we are not dealing with a perfect square trinomial when we factor this. So it looks like we have a perfect square with the a squared and the b squared. The AB part in the middle is not giving us a perfect square trinomial, so you need to be careful of that. Alright, let's take a look at an example or two and see how this plays out. So you can see x cubed plus 27. We know that 27 is 3 to the third power. So you can see here that once we identify that we have a perfect cube on both parts of the binomial, we take the part x plus 3 directly out of that, and then we have left over and we just follow the pattern above. With part B, you can see that we have a 2u squared that's common, so we need to take that out first before we can identify the perfect cube. So this has a second layer of factoring, just like you've seen in previous problems. So let's take a look at sample problem number 1. If you wouldn't mind stopping the video at this point, go ahead and try to follow the pattern that you saw above and see if you can work these two problems, and then come back and watch the solution. Alright, so 125 is 5 to the third power, and if you weren't sure of that, you could always use a function on your calculator. On your calculator you have a second function that looks like this with an n in the root, and you could just put 3 there for that, and you could do the third root of 125, and that would give you a positive 5. So if you're not comfortable with these yet, you can always use your calculator for the time being. So this is basically the same thing as x to the third plus 5 to the third. What I'm going to do is I'm going to drop the entire binomial that's embedded in there, the x plus the 5, straight out of that term, and I know it's going to leave me a trinomial. I know the front part of that trinomial is just going to be the remaining x's. So I had one x there, I've got 2 left over. I had 1 5 taken out, so I have 2 5s left over, so I have 5 squared. Now, this is where the signs and the term SOAP come in handy. We know that the first sign is opposite of the original sign, and then the last sign is always positive. Now, the middle term is a times b, which in this case is x times 5, So we would simply put 5x. Now, it would be appropriate for us to square the 5, so we're going to do a little simplification here. And that is our final simplification. Okay, let's look at part B. So you can see here we have an a that's common, and we can take the a out. And so we'll do that, and that gives us 64a to the third minus 27. Both 64 and 27 are perfect cubes, and so is a to the third. So we can break that up, and I'll just take an extra step here just so that you can see this. This is 4a to the third minus 3 to the third. Now I'm going to use my patterns to get that. So that's going to be 4a minus 3, and then that's going to leave me 4a squared. Notice I use parentheses there because the squared term has to go both 4 and the a. I have a remaining 3 squared. Again, that's always positive. The first sign in the trinomial is opposite of this, so I'm going to have a positive there, and then it's going to be multiplied of those two parts. So 4a times 3 is going to give me 12a. Now I need to come back in here and consolidate that trinomial, so I'm going to be left with the final response of 4a minus 3, 16a squared plus 12a plus 9. And that's our final answer. The next set of factoring problems that we're going to work on should look somewhat familiar, as they're in a quadratic form. So when you see an even degree polynomial, what you'll notice is that even degree polynomials can be factored similar to quadratic. So if we have something like x to the fourth, that breaks up into x squared and x squared, which is just simply x squared squared. So it just becomes a quadratic term. And we can do this with pretty much any even degree function. So this allows us to use our quadratic factoring that we learned in the previous unit on higher degree polynomials. So that's what we'll do here in the sample problem. So if you look at example problem 2, part A and B, you can see the different types of quadratic factoring that you've done with higher degree polynomials. So let's just go on to the examples. If you go ahead and work those and then come back and check out the solution. On example problem 2, what we have here is we technically have a difference of squares. 25 is a perfect square, x to the fourth is a perfect square, and negative 36 is a perfect square. So it's just like when we had difference of squares, we would break up each individual part. So we can see here 25x to the fourth will break up into 5x squared and 5x squared. 36 will break up into 6 and 6, and then since it was a difference of squares, that means we're going to have different signs. And so the difference here with factoring quadratic equations or quadratic expressions and factoring higher degree polynomials that are similar to quadratics is that we should always be looking for a second level of factoring to see if it's available. And in this case, it's not. 5x squared plus 6 cannot be factored, and 5x squared minus 6 can also not be factored. And so we will take a look at that each time. Okay, part B, we simply have an a and a b are values, variables across the expression, but b squared is the most common term. So we're going to take that out first. And that leaves us with a perfect square trinomial inside the parentheses. So if we take a look at that, we have a and a. 16b squared can be broken up into 4b and 4b. And since 16b squared is a positive term, that means we have two signs that are the same. And in this case, they'll both be negative, and of course we could rewrite that as a binomial squared. Alright, so there's some factoring, some quadratics factoring for higher degree polynomials.